Long before his name became synonymous with the atomic bomb, J. Robert Oppenheimer, alongside his student Hartland Snyder, delved into the ultimate fate of massive stars. In the late 1930s, the concept of super-dense neutron stars as supernova remnants was emerging. But Oppenheimer and Snyder asked a crucial question: what happens if a collapsing stellar core is too massive even for neutrons to hold it up? In their groundbreaking 1939 paper on continued gravitational contraction, they used Einstein's general relativity to model this extreme scenario. Their calculations painted a truly astonishing picture. They found that if a star's remnant core exceeded a certain mass, now known as the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 3 times our Sun's mass, no known physical force could halt its inward crush. Gravity would inevitably win. As the star contracted, Oppenheimer and Snyder showed that space-time around it would warp to an unimaginable degree. From the perspective of a distant observer, the star would appear to shrink, its light growing redder and dimmer, its surface clocks ticking ever slower. Eventually, it would seem to, quote, freeze at a critical boundary, the Schwarzschild radius, effectively vanishing from view. This was the birth of the concept of the event horizon, a point of no return. For an observer falling with the star, however, the collapse would continue unstoppably towards a central point of infinite density, a singularity. Within this event horizon, all paths in spacetime led inward. Escape, even for light, becomes physically impossible. Though initially met with some skepticism and overshadowed by the looming war, Oppenheimer and Snyder's paper laid the mathematical foundation for our understanding of black holes. It was the first rigorous, theoretical description of how such objects could form from stellar death. Decades later, as new astronomical discoveries like quasars emerged, their pioneering work was recognized as a cornerstone of black hole physics, forever linking Oppenheimer's name not just to earthly fire, but to the ultimate gravitational abyss. The cosmic giant we now know as TON 618 began its journey into our understanding as an unassuming, faint blue dot. Catalogued in 1957 by the Tonantzintla Observatory in Mexico, it was initially dismissed as just another distant star in our galaxy. But the 1960s and 70s brought the dawn of quasar science. Astronomers were discovering incredibly bright, distant objects powered by unseen forces. The true game-changer for TON 618 came with spectroscopy. When its light was analyzed, it revealed an immense redshift, meaning the light had traveled for billions of years, stretched by the expansion of the universe. This wasn't a nearby star at all. This colossal distance meant TON 618 had to be intrinsically, unbelievably luminous, far brighter than any single star or even entire galaxy. The broad emission lines in its spectrum were the telltale signature of a quasar, a supermassive black hole at the heart of a distant galaxy, furiously accreting matter and blazing across the cosmos. While its quasar nature was confirmed in the 1970s, the full, mind-boggling scale of its central engine came into focus later. Further observations and refined calculations revealed that TON 618 is powered by one of the most ultramassive black holes ever detected, weighing in at an astonishing 66 billion times the mass of our Sun. From a speck on a photographic plate to one of the most extreme objects known, TON 618's story is a testament to how our view of the universe can be transformed by new tools and deeper understanding.